We're starting our next unit on equilibrium. If you recall from thermodynamics and rates, we started to talk about reactions not just going from reactants to products, but that we could have reverse reactions going on where our products became reactants. And so when we look at equilibrium, we are looking at the point when the rate of the forward reaction and the rate of the reverse reaction are equal to each other. So both reactions are actually taking place at the same time, and eventually they get to a point where the rate of each of those reactions is the same. And that is the point where we would say that we are at equilibrium. So you can see in this diagram here that we have some of what is in solution here evaporating, and then in time they end up dissolving back into the solution. And so the forward and reverse reactions are both happening here. This is a demo that I did in class last semester. So both of these, it's hard to tell, but they both started off with about 100 mils of water each, and food coloring was added to one of the beakers just so that we could identify that as being separate from the water with no food coloring. And so I took pictures, I think it was about every 10 seconds. So you can see that we're a little bit under 100 mils over here and a little bit over on that one. And so what was happening was there were two different straws that they had different diameters. And so at the same rate, students were putting the straws into the beakers, putting their thumbs over the top, and then transferring into the opposite beaker. But because the straws were different diameters, there were different volumes that were being moved over. And so you can see here that we are significantly below 100 here now and significantly above in that beaker. And as we go on, we're getting to the point here where there's not really a whole lot of change going on. So this one's a bit blurry, but we seem to be sticking around 50 and 150. And I think this might be the last one. And so we're still at that same place. So for quite a few frames now, we've seen that there is no change in volume, and also the color has been fairly constant now. So this shows us what an equilibrium system looks like. Is the straws were still going back and forth, transferring water from one to the other. So we still have what would be analogous to our forward and reverse reaction rates occurring, but we don't see any changes happening. So anything that's observable, whether it's a volume or a temperature or a color, we don't see any changes there on the macroscopic level. But on the microscopic level, there are still reactions going on, both the forward and the reverse. And this is just a quick video to show you the same thing. So I just simulated the same experience, added in some food coloring, and started to transfer water over with two different diameter straws. And so this speeds up eventually so you can see quickly what is happening over time. There's small transfers going on at the same time, and eventually over time we see that the change in volume slows down as well as the change in color, and eventually there's not any difference in the color or the volume, even though the water is continuing to be transferred from one beaker to the next. Okay, so once equilibrium was reached, we had the same color and the volume then stayed constant. So they weren't the same as each other, but even with continual transfer with water, there was no change in the volume at that time. So once again, on the microscopic level, the forward and reverse reactions are occurring. They're occurring at the exact same rate, which is why we don't see any overall change on the macroscopic levels. Okay, so in principle, all chemical reactions are reversible, so they can move in the forward or reverse direction. And this one, if we were in class, we're able to show this happening with electricity. Unfortunately, that's not something we can do now, but maybe I can find a video of that. However, some things are not quite so easy. So each of these reactions, the reverse reaction would not be something that is easily reversible. So there are definitely some reactions that are much more likely to have forward and reverse reactions going on. And then we'll be looking later on at Le Chatelier's principle that we'll look at in different conditions, the forward reaction may be favored over the reverse, and then as we change those conditions, the reverse reaction may be favored over that. And that becomes important in industry so that we can create the conditions that are necessary to create whatever particular products we are looking for. So in grade 11 last year, we talked in stoichiometry about theoretical yields, and we talked about some of the reasons why an actual yield may be quite a bit lower than a theoretical yield, and we calculated percent yields. And that is only partially true, so sometimes there is a problem with the equipment that you're using, but there is also just the reality that some reactions are reversible, and so we don't go to completion. Not all reactants become products. The products then start to become reactants again. So if we have a system that is in equilibrium, we're not going to ever get anywhere close to 100% yield simply because we have both forward and reverse reaction rates going on at the same time. So we're going to take a look at what we refer to as the extent of a chemical reaction. So the ratio between the concentrations of products and reactants is going to become important to us at equilibrium. And every single reversible reaction or any system that can be at equilibrium has a different equilibrium constant at different temperatures. And that'll just determine the concentration of products to concentration of reactants ratio. So if we take a look at an example here, N2O4 decomposing into 2NO2. So the first one is colorless, NO2 is brown, so we could see a change through that. So if I start with no product, no reactant, no N2O4, and only NO2, which is my product in this reaction the way it's written, over time, my NO2 will get converted into N2O4, and I hit this point where from there on, my forward and reverse reaction rates are equal. They're steady, they're not changing any. And so that is when I've hit equilibrium. So over here where I start with N2O4 and no NO2, the N2O4 will slowly start to convert to NO2, and then at this point, both reactions are still continuing to happen. They just are happening at an equivalent rate. So there's no overall change that we can see. The concentrations remain consistent at that point. And then we could also start with some of each, the reactant and product. So this starts with both NO2 and N2O4. And so both reactions are going to occur once again until they level off. And so those are the points of equilibrium once the forward and reverse reaction rates are equal. So if we take a look at some concentration data from each of those, and there's more than just this that they would have gotten this information from. So with different initial concentrations of NO2 and N2O4, we end up with these concentrations of those compounds at equilibrium. So if I just take those concentrations and divide my product by my reactant, I get a bunch of different numbers here. But if I take NO2 and square it and divide by the concentration of N2O4, so each of these numbers squared divided by these numbers, then what you can see is I have a fairly similar number here for each of those. And that is the consistent ratio between products and reactants that I get at my equilibrium. And the reason this ends up being squared, if you recall from the last slide, the chemical equation was N2O4 decomposes to become 2NO2. And so this wasn't true in rates of reaction. We didn't use stoichiometry to help us set up our rate law. But in equilibrium, stoichiometry is how we set up our KEQ or our equilibrium constant expressions. So as we saw, it didn't matter whether we started with reactants, with products or with some of each, the same ratio of concentration ended up occurring at equilibrium. And so for a general reaction, so the lowercase letters, the A, B, C, D represent the coefficients, and P, Q, R, and S represent the different compounds. So the equilibrium constant, or KEQ, is my product compounds to the exponent, whatever their coefficient happens to be, and then over products. So P and Q are my reactants here, and A and B are my exponents. My coefficients become my exponents. So products over reactants is how I set up my KEQ expression. So we don't have any units here, unlike with the rate constant K, and this is all temperature dependent. So if I were to change the temperature of a particular chemical reaction, then the KEQ would be different for that as well. Okay, so products are always on top. So concentration of products over concentration of reactants using stoichiometry, or the coefficients, as the exponents. And we can only use the equilibrium concentrations in a KEQ expression. So this is only true when our system is at equilibrium. We can, however, use current concentrations and compare them to the KEQ to see if we're at equilibrium, and if not, do we need to move towards the products or towards the reactants to reach equilibrium? Well, we won't talk about that today. So once again, it's temperature dependent and there are no units. So as the temperature changes, the KEQ will also change, and that gets used in industry so that the particular compound that is desired is the one that ends up being created. Okay, so how do we set up these KEQ expressions? So let's take a look at some examples. So I have sulfur trioxide gas, SO3, decomposes into sulfur dioxide, SO2, and oxygen gas, O2, in an equilibrium reaction. Write the equilibrium constant expression. So the first thing I need is the chemical equation. So I have SO3 decomposing into SO2 and O2. And I have one sulfur, 3 oxygens, 2, 4 oxygens on this side. So I'm going to add in another SO3, which will increase my oxygens. That gives me 2 sulfur and 6 oxygen on this side. So now I'm going to need to add in a 2 over here, which gives me my 2 sulfur, and then 4, 5, 6 oxygen. So that's now balanced. So I need to have a balanced equation first, and then my KEQ, so concentration of my products over concentration of my reactants. So my products are SO2 and O2, and exponents-wise, I have a 2 or a square for my SO2 and a 1, or I'm going to write nothing in for O2. And over reactants is SO3, and my coefficient, which becomes my exponent, is going to be A2. So my KEQ expression for sulfur trioxide decomposing at a particular temperature is SO2 squared times the concentration of O2, all divided by the concentration of SO3 squared. Okay, let's look at another example that has some concentrations in it as well. So we'll come up with the KEQ expression and then also fill in numbers. So PCl5 decomposes into PCl3 and Cl2, and we have the following concentrations that are obtained at equilibrium. So 0.01 molar PCl5, 0.15 molar PCl3, and 0.37 molar chloride. So I've got all those up here. So our KEQ expression, the general equation, is there. So my products are PCl3 and Cl2. I have everything is a 1-to-1-to-1, so all exponents are going to be 1, and my reactant is PCl5. I'm going to plug in the concentrations for each of those and solve that. And once again, there are no units here. So 5.55 is the KEQ expression for that particular equation. And it is more than 1, so that means that I have more product, because products go on the top. So KEQ is greater than 1, which means that it is favoring the reactants, or it lies to, favoring the products, or it lies to the right is the other way that we would say that. Okay, practice questions to work on. So from the new textbook, page 428, numbers 1 to 5, and then